ignore that and hope I don't die. Too much information. Okay, so the halogenation is the next reaction that we are going to do. And just from experience, I don't know why they're drilling, but just from experience, what do you think is going to happen during a halogenation reaction? What are we going to add? A halogen, exactly. And in this case, a Br. So from what we've been doing in this chapter, specifically, where do you think we're going to add a halogen? The alpha position. Sweet. Okay, so we've already talked about this a couple times, but do we think alpha 1 or alpha 2 is going to win? Which position are we going to use? Alpha 2, sweet. Okay, I think so too. So, when we have a base catalyzed reaction and we're working with the enolate chemistry part of orgo, what is the base going to do? Yes, it is going to grab a proton. We're going to steal that hydrogen, give those electrons back. And throughout the semester, what have I been making you guys repeat over and over and over and over again? What does a base do? It makes a nucleophile more nucleophilic. So let's just make sure that that still holds true. So in this case, now we have Br2. And we have the negatively charged alpha carbon, right? And we already said that we're going to add a bromine to that alpha position. So what do you guys think the next step is going to be? C minus attacks the bromine. So let's do that. Bam. So then what would have to happen to this bond? It would have to break. Cool. So let's give those electrons over here. And so now we have H, and we also have Br. What do you guys think of this answer? Good? I think so too. The only thing is, I don't really expect you guys to know this, but some of you might. So, did this hydrogen become more or less acidic when we went from here to here? What do you guys think? Any guesses? It's a pretty even split. We got a few more votes for more acidic. And so I would also say it's more acidic. And the reason for that is because this bond is now even weaker than it was before. And the reason for that is not only do we have this carbonyl here that can stabilize this by resonance, we also have this halogen, which is going to suck up all the electrons through inductive effects. So it's taking all the electron density. So now this bond is super, super weak. So do we care? What is that going to do? What do you guys think? Am I just telling you guys this? And then someone asked a really great question. So if someone said, is this a chiral center now, and does that mean it can go through racemization? So yes, this is a chiral center now. However, we don't really care about chirality because we went from the non-chiral to the chiral. We can't tell if it's R or S or anything. So it is a chiral center, but we don't really care about it that much. And theoretically, it could undergo racemization, but he's not going to make you do like halogenation followed by racemization, that kind of thing. So theoretically it could, but we're not going to do that because it's mean. And then someone actually said that another bromine can be added, and that is true. So this exact same reaction can happen one more time. So that's what I mean by times one. And so if it happens one more time, all we're going to do is replace the second hydrogen with a bromine. Ta-da! So it's very, very important. I'm not going to draw the whole thing again because as I said, we're kind of going to do like a summarized version of these. But the reason we can go through this one more time is because we have our base catalyst still present, and the base can go ahead and steal that hydrogen super quickly and without using too much energy. So for that reason, we can go through the reaction one more time, and we can fully substitute this alpha center, or this alpha carbon, excuse me. And so what do I mean by fully substitute? We're replacing all the hydrogens with bromines. And then someone said, will this happen 100% of the time? So in chemistry, you can't really say that, but for the purposes of this class, yes. If you have a halogenation happening in base, we will substitute all of the hydrogens with bromines. And so this is a question that a couple students usually ask me each semester. After we fill this carbon, will we move on to the next one? For this class, no. In general, yes, that will happen. But for the purposes of this class, you just have to pick the more stable or the most favorable alpha carbon and only substitute that one. Don't touch the other alpha carbon. So what happens if we do this in acid? Well, we know that the purpose of the acid catalyst is usually to do what? Oh, and while you guys tell me that, someone asked, why is the hydrogen more acidic after the bromine is added? It is because the bromine steals a lot of this electron density, so it's stealing all the electrons for itself, making this bond super, super weak, which means that it's easier for a base to steal the hydrogen because this bond is so weak. Make sense? Okay, cool. So please remind me, humans, I don't know why I said that. What is the role of an acid catalyst usually? It makes the electrophile more electrophilic. Sweet. So we already said that this position is going to be kind of the nucleophile, but usually what does the protonating, what usually steals the hydrogen? That was such a weird way to phrase that. The oxygen. Thank you for getting what I said. All right. Also, it's 11:50, which means you guys are technically free to go. Since I came on 10 minutes late, I will stay for 10 extra minutes and just finish this stuff up. If you have to go, I understand. I'm recording, so the recording will be posted. Just please fill out the attendance sheet at some point. All right. So the oxygen will steal a hydrogen and become protonated, and it gets a plus charge. So what do we think the point is of protonating that carbonyl? Because we know we just want to do enolate chemistry anyway. So what do you all think the point is? And even if you don't know 100% and you want to take a guess, that's cool. I just want you guys to think about it a little bit. Can you guys hear the drilling? I apologize if you can. Okay, so the point of kind of making this positive is so that these hydrogens are a little bit more acidic. It's a little bit more favorable to steal them. So what do we think can come in and steal a hydrogen from this position? We have Br2 and we have H2O. What do you guys think? Water, exactly. So is water a terrific base? No, but it does the job. So it's going to come in, steal a hydrogen, give those electrons back. And so we get still a plus here. Now we got a minus here. And now we're pretty much in a similar boat as we were in the reaction above. So we have Br2. What can happen next? Yes, so this negative charge will attack the bromine and give those electrons to the other bromine. And then someone asked why didn't Br2 do it? So it could have also been Br2. It just depends on how you want to do the mechanism. I just like to use H2O as the base because that's what you guys are more accustomed to seeing, if that makes sense. Plus, oxygen is crazy. She does whatever she wants. Alrighty. Still have the plus sign, but now we have bromine and our hydrogen. So now what do we have to do in order to kind of have our stable product? Deprotonate. Cool. So now we have H3O plus. And what else do we have in solution? Aha, now we have Br minus. So we can deprotonate using the Br minus. Steal the hydrogen, give those electrons back. So now we get this lovely molecule. So are we done here? Oh, sorry. Are we done here? Nope. So why do you say no? Okay, so we can do it again. But let's just go ahead and see what the difference is between this and this are. Right? So in this case, we had base in our reaction that could go ahead and steal this hydrogen, right? In this case, what do we have left in solution? We have two different acids. We have H3O plus and HBr, right? So in order for this to react again, we have to protonate the carbonyl and then do all these different steps. That's not going to be very favorable, especially because we have this right here stealing all the electron density. So we already said it's going to take all that through inductive effect. That's also going to take some of this. So that means this lone pair is not going to want to be protonated in order to do the reaction again. So we are actually going to stop here, and this will be our final answer. And again, the difference is halogenation in base will be able to go more than one time and fully substitute. Halogenation in acid will not be able to happen multiple times, and you will stop after one addition. Any questions so far on that? Yes, I can zoom out. And someone said, what is the name of the product? Just the IUPAC name. So it'd be like 3-bromo something. You don't have to know it. I mean, okay. You kind of just have to know, like, in IUPAC how you would theoretically name that. But it's not any kind of special name that you guys have to memorize. Okay, and the last one I'm going to do, because it's in the same umbrella, I don't want to leave it to next week, is the haloform reaction. So the haloform is the same exact thing as a halogenation with base. The only difference is that now we have only one possible alpha carbon, and it has 3 hydrogens present. So what is the rule for a halogenation in base? How many times is it going to substitute? You guys are all saying 2, which is correct. But 2 is correct in this case. But there were only 2 hydrogens. So, okay, someone said fully, exactly, as many times as there are hydrogens on the stable alpha carbon. Awesome. So, while you guys are all correct, how I would say it is we are going to substitute as many times as we have hydrogens on the most stable alpha carbon. So in this case, we have only 1 alpha carbon, so that's our only choice. And there are 3 hydrogens. So we know that with a base, the first step is going to be steal that hydrogen, give those electrons. And we get a minus charge. The minus charge is going to attack the bromine. So we get 1 addition, and I'm going to do it in blue. Right? And so remind me one more time, how many more times are we going to do this reaction? 2 more for a total of 3. Awesome. So I'm going to say times 2. So we are going to get that fully substituted ketone. And now we have a special name for this thing. Can anyone guess what the special name for this reaction, or for this product right here is? Anyone want to take a guess? The haloform. Perfect. So right here, we're going to call this the haloform. And hold on, we're not done yet. But wait, there's more. So at this point, this bond is so terribly, I'll actually do it in red, is so terribly weak that this guy is actually going to be a really, really good leaving group because of how electron withdrawing it is. So it's going to take so much of that electron density that this is so unstable, we want to break this bond as soon as we can. So let's look around and see what we have left in our solution. So I purposely didn't write things down as we went. So I want you guys to look back and tell me what else is present in solution. We do have lots of H2O, true. Oh, what? H2O. We do have Br minus, but that Br minus could also be HBr, so I'm just going to say, their equilibrium. Both are present. But most importantly, we have OH minus. And we know that OH minus can act like a nucleophile, right? So if this were to act like a nucleophile, it could attack here and kick off our leaving group. And so what kind of reaction does this become at this point? We could call it SN2, but that's more of an orgo-1 term. What kind of orgo-2 reaction is this like? Yes, so it's like a nucleophilic acyl substitution. So we kicked off the leaving group, and if we used OH minus, what group am I adding here? An OH, perfect. And so what is this functional group called? A carboxylic acid, cool. And so you also have to note that we made CBr3 minus as our byproduct. And so the only reason I even give you the byproduct is because technically this product is at equilibrium with this. And so all this means is he could give you the carboxylic acid protonated or deprotonated. Both of those would be a correct answer for the product of this reaction. And I'm zooming out now so you guys can see the whole thing. I know this seems super long or kind of complicated, but just know it's very, very similar to the halogenations we just did. All you have to know is it's a little bit spicy because at the end, this whole thing will fall off and it becomes a carboxylic acid. I know that was a lot. Do you have any questions, comments, or concerns? So someone said, what about acid catalyzed? Wonderful question. So if we had this with an acid catalyst, we would stop here. So the haloform reaction will only happen when we have 3 alpha hydrogens on one side and a base catalyst. I'm actually really glad you brought that up. So we have our halogenation, which is kind of a big umbrella. Under that, we have base catalyzed and acid catalyzed, and our haloform. So our haloform reaction can only happen when we have an alpha carbon with 3 hydrogens, and we have a base catalyst. And a little asterisk by that alpha carbon, because we have to have 3 hydrogens on our most stable alpha carbon. So in this case, this alpha carbon is not available. So the only option we have is this guy. Another example would be if we had this symmetrical ketone. These are exactly the same. So this could undergo the haloform reaction, something like this, or something like this. So these could all undergo the haloform reaction, or anything that kind of looks like that, where all we have is a primary carbon for our alpha position. And someone said, so if there's 3 hydrogens, we add the bromine on 3 times? Exactly. The reason we didn't do that here, though, is because even though there's 3 hydrogens, on the other side, we have a better alpha position with only 2 hydrogens. So that's kind of the difference that I wanted to show you guys. I don't know why my screen went crazy for a second, but I zoomed out just so you guys can see it. And that's all I'm going to cover today. I apologize again for being a little bit late. Let me know if you have any questions or anything. And I accidentally started recording like halfway through the session. So whatever didn't get recorded, I will just do again for you guys. And I'll record it and I'll post that. Thank you. Happy Thanksgiving for all of you guys. Sorry, what was that?
Sorry, I have a question.
Yeah, what's up?
Okay, so I think I missed the explanation, but what was the difference between the acid and base catalyst for the halogenation?
Great question. So the only difference between the acid and the base, or the base and the acid, is that the base catalyst is going to take this hydrogen easier. It's going to be a lot easier. So we can do multiple substitutions, whereas it's a lot harder to take that hydrogen with an acid catalyst. So we're only able to substitute it once. Therefore, when we do the haloform reaction, it's only possible in base because we can only substitute one time anyway with an acid.
Okay, that makes sense. Thank you.
Cool. You're very welcome. Bye. Have a nice long weekend. Get some rest or get some studying done, whatever you guys are going to do. Stay safe. Don't get COVID. So if someone asked, wasn't there another reaction where the acid went to full substitution or went longer than the base? Yes, that was in the acetal-ketol reaction. So the acid catalyzed went all the way to the acetal or the ketol, and the base catalyzed stopped at the hemi. So yes, you're right. I'm really glad that you are connecting the dots. Makes me so proud.